Okay, so conduction in steady state in beyond one dimension. So let's see what we have for this. We're wrapping this up today. Oops, no, not this one. I don't know what happened here. Sure. Okay. Sure. Okay. So I assume you guys are seeing the example of overall heat transfer coefficient in a pipe here, chat. Okay, good. So what did we see so far? We saw that the concept of thermal resistance could be generalized to spheres, to cylinders, and then we looked at heat transfer coefficient. We had the concept of overall heat transfer coefficient. That is what we use in heat exchangers or in construction materials, for which you also have a list in this handout. So if you want to calculate the overall heat transfer coefficient of the windows in your house. And then we talked about isotherms and adiabats. And about that, I wanted to share a few images with you that are cool, that I think they can help to get the concepts in better. Isotherms are lines of constant temperature. Adiabats are lines of flow of heat by conduction. And isotherms never cross other isotherms, and adiabats never cross other adiabats, but isotherms and adiabats always cross at 90 degrees. And this an insulated surface is an adiabat, and all the adiabats will be parallel to the adiabats will be parallel to that, will never cross it, and isotherms would land at 90 degrees against the insulated surface. Conversely, isothermal, a surface of constant temperature as a boundary condition will have the isotherms next to it parallel, and the adiabats will be at 90 degrees of it. So let's see. You are quite familiar with this type of isotherms, right? These are the lines of constant temperature in a map. Now, weather is more about advection than about conduction. I'm showing you these isotherms just so you see that it's a concept that even people with no education kind of makes sense, right? What moves these isotherms on the map is not so much conduction, but winds, and that's all about advection. But here we have some isotherms. Now, these are isotherms of conduction. We get to see colors here, and the isotherms in this type of images are given by the isotherms in this type of images are given by different by different colors. So everything that has the same color is at the same temperature. And typically in this type of images, we have the reds represent hot, the blues represent cold. This is a heat sink, right? Much like we have been using for other examples or for assignment 1. And we get to see how what would be on top if this is the heat sink for, we don't know what this is for, but let's say it's for electronics. The electronic component is hot and the heat is coming out through this kind of tree of fins. isotherms as lines, right, are illustrated in this image here. We might have a heat source here that is on an insulated surface. And in this case, the heat is going to flow away from the heat source. So they call it flow lines, but those are adiabats. You get to see there, well, I haven't talked about the isotherms yet, but here are the isotherms that are radiating as if it was like waves coming out in a pond, right? These are the isotherms. And you get to see that the adiabats are perpendicular to the isotherms. You also get to see that if this top surface is insulated, this line becomes an adiabat, and that means that the isotherms are perpendicular to it, as you get to see here. These schematics give us a lot of insight about how the heat goes from where to where, and where we would expect more concentrations or more distributed heat, where we could expect high temperatures or low temperatures or uniform temperatures. So these graphs here that look so simple, in reality are very full of insight. This you see here is a problem from one of the quizzes in previous years. And we had discussed this. This is in a heat conduction inside a plane wall. And we see one side of the wall has a temperature, in this case 60 degrees. The other side of the wall has this other temperature, in this case 20 degrees. The heat would flow from one to the other side. And because the heat doesn't flow like in the plane of this wall, this is 1D heat transfer. The wall is 2D, but the heat transfer is 1D because it goes in only one direction. The isotherms are parallel to the surfaces of the wall, and because this wall is insulated on top and insulated in the bottom, they're perpendicular to the bottom too. So this is a very simple problem for isotherms and adiabats. This is a more complex problem. In this problem, I gave the isotherms that are these lines here, and I asked to draw the adiabats going through each of these points. So what do we know? We know the adiabats are perpendicular to the isotherms. So going through this point, I would go through everything that is perpendicular. If I'm assuming that the center, like I'm saying, this is the maximum temperature at the center, so this is moving out. So for those of you in MADI, this is the temperature distribution from continuous casting, during cooling in continuous casting of steel or aluminum. Actually, I got this image from a paper. So here we get to see these isotherms. We would make an adiabat that looks very much similar. And the surface temperature, this is the temperature of the mold, is uniform. So the adiabats are perpendicular. And here the line of flow of heat would be perpendicular to these curved lines, and eventually would end up being perpendicular to this side or this other side, right? If we do the differential equation, we would see that with these boundary conditions, we have a singularity at this point, in which just a little bit to the left is always perpendicular getting out, and a little bit below this point is always perpendicular aiming to the right. And here we have yet another isotherm that goes straight out. And in this point here is a singularity again. So in reality, what we see here as a line is a very, very, very narrow ellipse. So here you have an example of an adiabat in a previous exam. Here you have isotherms, and you have this arbitrary shape that is insulated on both ends. And we have now this surface on the top and in the bottom are at the same, at constant temperature. So the isotherms would be something that more or less follows the contour, never crossing each other. We're doing them intuitively and by hand. And by the way, it's never going to be too bad, right? Because the geometry takes us ourselves. After we have done the isotherms, if we wanted, we could do the adiabats too, right? We don't need to worry about those now, but we could. How would those be? Let me see. You draw. Okay. So the adiabats would be things like this, assuming that T1 is higher than T2. And this adiabat is kind of ugly. I made it here. Let's make it better. Much better now. So, and where we go. Here we go. Okay. Here we have, I'll need to erase all these ugly lines I made here. So, and we'll discuss this other case later. So let's go back to our calculation of shape factors. So what happened here with the mouse? I lost my mouse. Okay, so let's go back to okay, so let's share this. Okay. Window. Okay, so we saw this case here of a pipe. And we talked about adiabats and isotherms and adiabats. And then we talked about thermal resistance of systems of an arbitrary shape. And we introduced the concept of the shape factor. And the shape factor was a way of predicting thermal resistance using tabulated values done by people who spend lots of years working on each problem. So we know how to work with resistance, and we define the resistance, and And we define the resistance now based on a shape factor and a thermal conductivity. This would apply to every other thermal resistances we have seen so far. So you can calculate a shape factor for a cylinder or a plane wall or a sphere, but we already did. So although we can do it, we can calculate the shape factor, it's not as useful as when we calculate very complex geometries, such as these ones that we have here. For example, when I mentioned the case of something that would resemble SAG-D. And so let's discuss. There is another way of calculating the shape factor that I want to discuss now. And then I want to do an example. So the shape factor can also be calculated using this dimensionless conduction rate. And for using this dimensionless conduction rate, we need to use the surface area of the body, whatever it is, and a characteristic length. And the characteristic length tends to involve the surface area again. So all this part here essentially is all depending on the surface area. And this dimensionless conduction rate is typically used for things that are finite in size, something that is not infinitely long like a pipe or infinitely wide as a wall. And this dimensionless conduction rate is also tabulated, for example, for the case of a sphere. And something to keep in mind, something I might ask, you see here we have the dimensionless conduction rate for a sphere and here we have a sphere buried in a semi-infinite medium. We can have a dimensionless conduction rate associated to this, same as a shape factor, because this formula that relates both of those. And we can have an infinitely thin rectangle under it, in an infinite medium, right? And we have dimensionless conduction rates, or for example, if we were to have a hot cube inside an infinite volume, right? All these four examples here are inside infinite volumes. Okay, so let's talk about a problem in concrete, and very interesting problem. That is not in the book. That I prepared this problem based on my conversations with people in the field of oil and gas. So I mentioned to you in previous classes that you get to see where the pipelines go under the ground because the heat of the pipeline makes the grass greener, right? So let's calculate a little bit about this heat transfer from the pipeline to the surface. Let's start with this. Where does the heat of the pipeline come from? Because nobody heats up the fluid, right? I know that in the oil sands, sometimes we heat it to have it more fluid. But what happens in pipelines is the frictional loss. The pressure losses are energy that is transformed into heat. And that heat is what heats up the fluid. Now, that heat doesn't accumulate forever. That heat actually flows through the soil to the surface. And this is what the problem is about. So I want to do two things. One is by knowing the pressure losses, I can estimate the heat. Therefore, I should be able to estimate at what surface at what temperature the surface of the pipe is. And also using our knowledge from thermal resistance, I want to know how the temperature of the fluid and the temperature of the soil are related. Are they similar? Are they not? So let's do it. We have here in this problem, we have the pressure loss. We have the pressure loss that is about 5 times 10 to the 6 pascals. That's actually quite a bit of pressure loss. An atmosphere is 10 to the 5 pascals. right? So this is 50 atmospheres. It's a lot. But it's 100 kilometers of pipe. The outer diameter of the pipeline is 30 inches. So these are like realistic values. And here is a thickness of the pipe that is 7.92 millimeters. Let's say that the surface of the ground is at 20 degrees C. Let's say for this example, and that is constant. Very realistic for something in our spring and summer, and or summer and fall, right? I have the thermal conductivity of the soil here that is tabulated, that is more or less known and depends on the type of soil you have, but this is representative of what we have in Alberta, and the thermal conductivity of a steel. We have the flow rate of this pipe. All these numbers are numbers that people from oil and gas gave to me. And the convection coefficient of the pipe, I put 300 watts per meter square Kelvin. We will learn how to calculate this number with more accuracy, but this is a reasonable number for the convection coefficient of the oil inside a pipe. You know? And I'm talking about a flow fully developed thermally and in steady state. Steady state, you know what that is. Fully developed, you might know from fluid mechanics, but when we study internal convection, we'll get deep into what a fully developed flow is. So here we have a schematic. Here is the surface. Here is the pipeline underground, and this is the outer surface of the pipe at 30 inches. And let's say that this the soil in contact with the pipe is at TS1. The surface of the soil is at TS2 here. So let's do the calculation, and let's start with what we know. Let's start by doing a control volume and an energy balance. So in this control volume, I'm calculating everything that is happening in the pipe and inside the pipe, right? So what is outside the control volume is just soil. And we have heat that comes in by advection, heat that goes out by advection. We also have heat that goes by conduction through the soil to the surface. On Monday, I will be asking you why we are not considering conduction heat transfer in the longitudinal direction. Can anybody tell me through the chat if I'm doing, well, I am doing a good job by not calculating conduction heat transfer in the longitudinal direction in a pipe. Why? It's something we did discuss in class. I'd like to see if any of you can have a quick look at the notes. Well, this is an excellent answer. The temperature on both ends are the same. And if temperature on both ends are the same, there is no conduction. So what you said is true. But if the temperature on both ends were different, we still would not account for conduction. So this is part of what goes on Monday. Yanni's part. I imagine that the notes on differential control volumes are quite abstract, but for example, if you take a look there, you'll see that we discussed the Peclet number. And the Peclet number is the relationship, the ratio of advection to conduction. And what we saw is that for pretty much any normal pipe, right? If you calculate the Peclet number that you have to calculate it, I'm not doing it here because I know it all too well for the case of pipelines, you get that the Peclet number is enormous. And an enormous Peclet number means longitudinally is completely dominated by advection. And that's why we didn't include conduction in the longitudinal direction. please check out. Peclet number and Biot number will be things we discuss on the exam, on the quiz on Monday. So now that we have this control volume, we can write our energy balance. Q in minus Q out plus Q generated equals Q stored. Q in would be Q in by advection, and that is, this is volumetric flow, right? And times density times the enthalpy of the fluid coming in. What goes out? What goes out is heat by advection, and also this heat that goes out by conduction through the soil. So advection will be the volumetric flow times the density times the enthalpy at which it goes out. What goes out by conduction? In this case, we're going to use the concept of shape factor. If we needed to solve this without the concept of shape factor, we would need to do like very complex math or a finite element analysis. So this is the important part of the class, and this is the important part of this unit. In this case, we wouldn't, that we're in steady state, and in the soil has no heat generation. The pipe has heat generation, but the soil doesn't. If we write the partial differential equation, we can simplify a little bit. And after we simplify it, it's still a nightmare. But somebody solved that nightmare. Somebody spent 4 years of a PhD doing it. And that is all contained in this letter S. When I write this, it looks just like a small annoyance of algebra. In reality, when I'm putting this, I'm saying I'm going to stand on the shoulders of these people who spend so much time solving these partial differential equations, so I don't do it, and so you don't do it. And we should be very grateful for that. Okay, so we got the heat that comes out by advection, and we got the heat that comes out by conduction through the soil. We don't know exactly what this S is yet, but we know that we are never going to be wrong, because whatever the shape is, there is an S associated with it. And the temperature difference is TS1, the temperature of the soil right against the pipe, and TS2 is the temperature of the surface of the ground. And Q generated. Now, in this control volume, look at this control volume. This control volume, inside there is heat generation. And the heat generation is something you already know. I'm not going to be testing you on that, because this is heat transfer, but it's not fluid mechanics. But the energy loss is the pressure loss times the volumetric flow. That gives us watts. And this is the energy generated. And we know it. And people know it because you're measuring it all the time in the pumping stations. And we know that was 50 atmospheres times the volumetric flow, and gives us a lot of watts. So just think of this. Pipelines are the most economic means of transporting like fluids, yet they consume a lot of energy anyway. We are going to assume we're in steady state, right? So the Q stored is going to be 0 because we're in steady state and things don't change with time. So I grab all these that we have calculated based on our knowledge of the first week of class. Look, this is first week of class. First week of class, up to here is first week of class. This we have here is this week in which we use the shape factor to calculate conduction in a weird geometry. That is conduction from the pipe surface, from this hole, to the surface here. Heat generation, that is actually fluid mechanics, we put it all together and we have volumetric flow times density times enthalpy coming in and enthalpy coming out. And now is when we got this suggestion that the temperature in and out through our control volume is the same, right? Then I apply that, and this enthalpy coming in and this enthalpy coming out by advection go away. And what we have is this aspect of energy loss that was conduction through the soil and the energy, the heat being generated. If I solve for this, I can calculate this TS1. I can calculate the temperature of the soil surrounding the pipe just by solving this. I need S, and this value of S, let's see if we have it. Okay, okay, let's see. Here we go. Isothermal cylinder of length L buried in a semi-infinite medium. Okay, so we're gonna assume that the Earth is a semi-infinite medium. And here we have our cylinder of length L that between pumping stations was 100 kilometers. And here we have two possible solutions. In both solutions, and this is something we have to do forever in this class, we're gonna get formulas that somebody did for us, but that somebody needed to cut some corners at some point, saying, for example, the cylinder is much longer than its diameter, right? We must check that that is true. In the case of a pipeline, that's pretty much trivial. The pipeline is 100 kilometers versus 30 inches, but it's not always the case, and sometimes it's not obvious. So we must check the restrictions before we use each of these formulas that some saint did for us. So length much bigger than diameter. That's a check for either of the solutions. Now it says, how deep is it? For any depth, we have this formula here. But if the depth is bigger than 3/2 diameters, right? And the depth we said was 2 meters and the diameter was 70 centimeters, give or take. So we are deeper than what says here. We can use this other formula that uses a log instead of a reciprocal hyperbolic cosine. We don't want the arc hyperbolic cosine, although our calculators have it. So because I'm in this condition in which the depth is bigger than 3/2 diameters, I am going to use this formula. If I didn't match these conditions, you see that each of them has a restriction. If I don't match these restrictions by a little bit, maybe I'm okay. I'm starting to accrue error, but it's kind of okay. If I don't match this condition by a long shot, chances are that the results are going to be quite off. So we're going to do this in convection. You're going to see this happens all the time. And they ask us, is the flow turbulent or laminar? Is the flow fully developed or entry flow? We're going to see those things later down the road. So we check the two conditions, and here we have our formula. And in our formula, we can calculate now the shape factor, 2 pi L over log of 4ZD. This is exactly what was in the table and what is in the formula sheets that we prepared for previous years and you can use now. And replace the numbers and we get this shape factor that has units of meters, whatever those are, right? And the outer temperature, then we would calculate replacing this shape factor in here, and gives us that the surface of the soil, right? Remember that this is conduction is right outside the control volume all the way to the surface, right outside the control volume. This is the temperature of the soil, is nearly 40 degrees C. I'm talking about the surface of the soil in contact with the pipe. But by the way, you should know that that's pretty much the temperature of the fluid. That's what but how do we know? How do we know? All right, let's check it out. So here I have, if we pick the outer surface of the pipe, this gives us this heat rate that is 11.5 watts per meter square. We can also calculate an overall heat transfer coefficient, which I did it separately. And the overall heat transfer coefficient is actually quite low. The overall heat transfer coefficient, if the reference surface is the outer diameter of the pipe, is 0.58 watt per meter square Kelvin. It's fairly low, right? Natural convection would be 10, and this is 5% of natural convection. So the soil is a pretty good insulator for the pipe. Okay, how do we know if the temperature of the fluid? Because we know the temperature of the soil just outside the pipe. So we can we can look at the equivalent circuit, and we know we would have the resistance of convection of the thermal resistance of convection of the pipe inside, the thermal resistance of conduction through the pipe, thermal resistance of conduction through the soil, and then thermal resistance of convection outside on the surface towards the air on top. So let's say now that the air outside the pipe was at 20 degrees C, and let's say the fluid was more or less at 40, right? So let's calculate each of these thermal resistances. You see, I put a prime because being a pipe, we like to do it per unit length. So resistance of convection inside is 1 over H area. The area would be pi diameter internal times length. And because it's resistance per unit length, I need to multiply by length. And that's why we see no length in here. The resistance per unit length of the pipe, we saw it is using this log, is this expression here. And we can calculate this other one. Look at how small it is. Convection is more or less 10 to the minus 3. This is more or less 10 to the minus 5. The pipe in general, the pipes, especially in heat exchangers, the thermal resistance is very low. Thermal resistance per unit length of the soil would be the resistance that was 1 over SK times L. And we replace these values here and look at what we get. This resistance per unit length is 0.7, right? 10 minus 3, 10 minus 4, 5, almost 1. Enormous. Resistance of convection on the surface would be, here would be length and divided and the H of the surface, that is more or less 10, but by a width that is infinite. So this is essentially 0 because we have a very large width. So what do we see here? Can anybody suggest? I would like to see in the chat if anybody spots a dominant resistance and which one. So I would like to hear, is there a dominant resistance and which one? So I'm going to go over this again. We have a series circuit. Yeah, absolutely. The soil is the dominant resistance. See, it's a series circuit, and this is much bigger than all others. Now, this has implications because, well, if this thermal resistance is 0, let's start with convection on the surface. If this thermal resistance is 0, that means that this point here, the surface of the soil, is at same temperature, 20 degrees C, as we said at the beginning. Right? And of course it makes sense, right? The soil is more or less at the temperature of the air. Now, we see that this resistance of the soil is big, and these other resistances, convection inside the pipe and resistance of conduction through the wall of the pipe, are small. So if these are very small, I cannot say these are more or less 0. And what does it mean? That the temperature of the fluid here is more or less the same temperature of the inner part of the soil. So when we calculated pretty much 40 degrees for the temperature of the soil, because the resistance of convection and the resistance of conduction through the pipe are so small, that means that the fluid inside the pipe is more or less at the same resistance that the inner surface, this part of the soil. We can say that only because these resistances, convection and conduction through the pipe, are so small. If you look at problems in previous years, we went over this exams in previous years, we went over this example quite a bit. You can expect something similar. Might not be a pipeline, might be something else, but this type of analysis to come up. We talked briefly last time about thermal resistance of a beer cooler, right? Let's say it's made out of styrofoam and it has relatively thick walls. What if, for example, the pipe is very close to our soil? What if, for example, the pipe is very close to... if the resistance of the pipe... Okay, excellent question. We can account for all of that. Imagine the resistance of the pipe is comparable to the resistance of the soil, right? So how can we explain this? Okay, let's try to do it the best possible way. Okay, I'm gonna give it a try. So so the question is, what if the resistance of the pipe is more or less, if this resistance is more or less the same as the resistance of the soil? So let's say this is still small. Let's say this is still small. And we have an amount of heat Q per unit length here, right? So if we said for this amount of Q, this difference was, we had 40 degrees here at this point, right? And we had 20 degrees here. This one went away, right? And we had 20 degrees here. So we have a jump of 20 degrees over the soil. The soil gives us delta T of the soil is 20 degrees C. If the resistance of the pipe is more or less as the resistance of the soil, right? So we would have delta T of the pipe would be R times Q, right? And we know that Q was delta T in the soil over R of the soil, right? And this is R of pipe. So if I were to replace this value of Q calculated inside this delta T for the pipe, right, we would get that delta T of the pipe, if the thermal resistance of the pipe was the same as the thermal resistance of the soil, would be more or less the same one as that of the soil. That would be 20 degrees C. If this resistance of the pipe was similar to resistance of the soil, the temperature of the fluid would not be 40 degrees, would be an extra 20 degrees, would be 60 degrees C. Because now the heat needs to go through two big resistances, not just one, and the pipe can accumulate more heat then from the frictional heating. Did this help? Okay, excellent, excellent. So let's see. We had already discussed this. I think actually we completed everything we wanted for the class. This example for the beer cooler is just similar thing using the values from this table. This case 8 and case 9. It is 1:50. I'm gonna take a 10-minute break and I'm gonna be back here at 2 for office hours. And I hope some of you will join me too. I'll see you then. Thank you very much.